Hi, I'm Tony Williams. I'm the architect of OLE. I'm going to talk about the principles of OLE, Microsoft's Object-Oriented Systems Architecture. I'll talk about the rationale behind these principles, how we apply them in practice, and how this affects the resulting system. OLE is a term whose origin is only of historical interest, somewhat like ACM and 3M. OLE derives from the acronym for Object Linking and Embedding. ACM is for Association for Computing Machinery. Minnesota Mining and Manufacturing is 3M. The origins are not particularly relevant to what they mean today. The OLE architecture is Microsoft's architecture for structuring software in a heterogeneous, distributed computing environment. This architecture uses abstractions as a system structuring mechanism. This is similar to the way that we use objects to structure applications, but there are some differences because we're talking about a system. In particular, an open system means we need to support asynchronous evolution of the parts that make up that system. Real-world systems cannot be switched off to upgrade them. So the OLE architecture is built on object-oriented technology, and I'll talk about how we apply that to this particular problem. OLE is an architecture for interoperability between software components. It's the network interoperability between machines and between operating systems. It's for application interoperability, with services provided by the operating system, other applications, and other service providers. It's for integration of applications in carrying out a single task for a user or a business. OLE provides the glue code that binds these pieces together to make a useful system. OLE is not a language. It is not a language extension. It is not a framework of the kind that we see with class libraries that are used to help build software. And OLE is not an operating system. It is the architecture by which different frameworks and languages can interoperate. I'll talk here about one of the thought experiments that we did when we're designing OLE. Imagine I'm working on a document when I take a break and go for lunch, leaving the document open on my screen. While I'm at lunch, my friend tells me about a great new drawing package that he's seen. So I go out and buy that package and come back and install it onto my machine while my document is still open. Back in my document, I say Insert Object. And there is my new draw package in the list of things that I can insert. This is a very flexible dynamic binding and dynamic extensibility of a single document application. OLE makes that real. Here I have a graphic that shows the overall structure of OLE. It's a multi-layered architecture. The underlying technology is the component object model and the RPC system that I'll be talking about in detail. Layered above that, we have models for storage and naming, data transfer and automation in the interfaces, which is how applications communicate data between themselves and invoke operations on each other. At the upper level, we have the compound document user interface, where we provide a style guide and interfaces for negotiation about user interface resources, such as screen space, menus, toolbars, and so on. The requirements that we saw as being placed on this overall model are as follows. The model must be scalable. We want a uniform programming model for dealing with very large objects and very small objects. A push button on a form or a text field in a dialog versus a large table in a back-end mainframe database. We want a common programming model for those things. This model must be efficient for dealing with the small objects so that we can get the same dynamic extensibility both in our forms model and in our large-scale document and data models. This model must also be capable of dealing with very large numbers of objects. In a global enterprise network, you can imagine 10 to the 8, 10 to the 9 or larger numbers of objects. The system must be robust. Given that we have evolution of the system and different pieces are replaced at different times, we must not have any artificial introduction of error cases because of this asynchronous evolution. So the system must support changeability while retaining compatibility with what's there. Primarily, the requirement we saw was for extensibility. We could not afford to build a system that constrains us to a lowest common denominator. The system must be able to evolve over time and get richer and provide more function without having to stop and rebuild. So, OLE provides an object model, which is a kind of meta-architecture, and it provides a set of related architectures that define relationships between objects. And it provides a set of services that can be used in the collaborations that take place in those relationships. I'll talk about each of these. The object model defines a set of characteristics that apply to all objects independently of what kind of objects they are. This covers things like identity, instantiation, and so on. It's also a set of services that are provided for all objects, such as naming, binding, activation, and contract negotiation. Of the set of related architectures that are used in the domain of compound documents, we have storage containment, because objects may live inside some containing document or separately in their own storage unit. We have visual containment, so that objects can be presented in the context of the containing document and activated and edited there. We have data dependency between objects and data transfer between them. We have procedural composition for scripting languages and custom applications. These architectures have been designed to be separate even though they're related, so that they can be recombined with other approaches. For example, I may want to evolve to a world where I store my document elements in a database, but I still use the visual containment architecture that's been defined in OLE. Finally, OLE provides a set of services that can be used in these architectures. We have a storage service that provides a hierarchical set of independent storage units for objects that all live within a single file. This allows us to provide the illusion of separate storages for these objects, even though at the operating system level the document is stored as a single entity. Similarly, we provide a network RPC so that objects can be distributed across the network and still communicate as if they were local. And we provide a set of services for compound document support specifically, things like maintaining cached representations of objects so that they can be viewed and printed without having the object server implementation present. Now I want to talk at some length about the component object model that underlies all this, and go into some detail on the principles that we used in designing it and how we put them into practice. This component object model's driving motivation is to support interchangeable parts so that I can replace an implementation, for example, of a small table in memory, replace it with some large database, and have all the clients that are using that service not know the difference. We want to support the evolution of parts in an open world and evolution of the kinds of integration between pieces. So this extensibility that we get allows us to introduce new kinds of objects which provide new services and new interfaces for talking to those services, and thus richer integration between pieces. An object encapsulates information. This is a key part of the way we approach our design. We encapsulate some state and the implementation decisions that the implementer chose to take when he was building his object. Normally, the state and the implementation decisions go together. Some pieces of state may be exposed through an interface, but that's a separate issue. A key part of this is that we separate the definition of the interface from the implementation of the service that provides it. This is a concept that's well known in the world of programming with abstract data types, but it seems to be much less well understood in the object-oriented programming community. It has great value, and I'll talk about it as we go through this presentation. The first major point is that an interface represents a contract. It's a commitment to provide certain function and to conform to certain rules. The interface designer specifies that contract. The service provider who's building an object implementation chooses to implement that contract. Some client chooses to use that interface in order to achieve his goals and to conform to his side of that contract. We have a mixture of formal and informal definitions of contract and the agreement to meet it. But the key thing that we need when we have a dynamic binding and evolution of these objects is that when one object meets another one, we have a formal way to ask the question, did we agree on the same contract? And that's a key element in our design. Part of what we require in order to do this is the notion of a runtime interface identifier that can be used in this formal negotiation process. These identifiers must be unique. In addition, since we allow for anyone to define a new interface, we need a way to assign these identifiers without going through a central authority. We use the DCE Universally Unique ID scheme for this. Having separated interfaces from implementations, we then observe that we really want to have multiple interfaces for a single object. We want polymorphism of objects in many dimensions. For example, some part of my program may wish to deal with objects as regards to persistence, independently of what types of objects they are and what other capabilities they have. So we need a mechanism that allows one class to expose multiple interfaces and yet retain the single identity of that object. The mechanism that we introduced for this is known as query interface. This is a method that is supported by all objects. The model for this is that the class implementer knows at the time he builds his implementation what interfaces he implements. Similarly, the client implementer knows the set of interfaces that he can use. The query interface method passes in an interface identifier and simultaneously asks whether this interface is supported, and if so, retrieves access to the dispatch table for that interface. Interfaces have a binary standard representation on any given platform. We define a standard for interface identifiers, for dispatch tables, for calling conventions, and for dynamic code loading. Having a binary standard allows this efficient support for small objects. That means small objects can be implemented by code that's loaded dynamically into the address space of the program that wants to use it. Then there's no overhead in accessing that object. A part of the component object model that we designed early on is based on the notion that the code that instantiates an object has different requirements and knowledge than the code that uses an object. We provide creation functions to create these objects rather than constructors of the form that C++ has. This separates knowledge of the actual class that is created from the code that calls that function and decouples them to a certain degree. We also use two-phase construction. We create an instance of an object and then we initialize it. There are two reasons for doing this. First is that different objects in different scenarios will have different initialization interfaces. Some may be initialized from storage, others may be initialized from parameters supplied by the creator. The other reason is for error handling. We need a way to be able to robustly signal errors back to the caller. Constructors in programming languages do not have good ways to signal errors back. A key part of our design goal was that programmers should be able to build their system with abstractions without simultaneously having to adopt new programming paradigms such as exception handling, garbage collection, and concurrency. One of the things that we gain by clearly separating interfaces from implementations is the ability to support what we call virtual objects. These are things that appear as objects to their clients, but are not necessarily implemented as objects. They may instead be part of some larger structure and not have a separate existence in storage or implementation. This allows two things. It allows efficiency of implementation, so that we can have a cell in a table or a spreadsheet that is being used as an object, but is not implemented as an object. It also allows us to build compatibility with a lot of existing application structures, so that rather than re-engineering our spreadsheets and databases to talk about lots of fine-grained objects, we simply provide the virtual object layer on top of existing implementations. I'm going to move on now from talking about component object model and talk about some of the design themes that recurred in the OLE architecture. There are a number of issues that I want to talk about. One is factoring function and design decision into separate objects, so that we achieve some given function through collaboration of a number of separate pieces. We have parametric implementations, so that any given object that's designed to be parametric can be customized to a particular usage. All of these things give us reuse of design and reuse of implementation of parts and customizability of parts so that they can be better reused. The first point is factoring, otherwise known as functional decomposition. We take a given problem and we want to factor it into two or more pieces and encapsulate the particular representations and decisions within each of the objects. To do this, we need to introduce some intermediate interface or representation in order that we can get collaboration between these two separate objects. The value of doing this is that one or other of the objects can be replaced to provide a different collaboration and get a different end result. This is a form of reuse of one of those objects. With parameterized objects, the model is that one object will create or obtain some resource and give access to a second object, which then uses it. For example, a drawing surface object can be instantiated by one object and given to another one. The second one will then use that surface for all of its drawing. This allows the first object to customize the behavior of the second object for its own purposes. One of the interesting things about our component object model is that having done this, the receiving object that's getting this resource can negotiate more interfaces with it, so that if certain types of resources are allocated, that object can make use of additional functionality that perhaps even the creator didn't know was there. For example, an object may know how to optimize drawing to a certain kind of printer. One of the things that we see is the recurrent use of a given interface in lots of different collaborations. This supports reuse of design, because once we've identified that we can use the same interface, there's a lot of design work we don't need to redo. It supports reuse of implementation, because a given object that supports this interface may be used in multiple collaborations. Similarly, a client that uses some interface to provide some functionality can operate uniformly over multiple different objects that provide that interface. I'll talk about some examples that occur in OLE and how these principles show up in these examples. Things I'm going to cover are remote procedure call, custom marshalling, persistence of objects, containment and naming, and uniform data transfer. This diagram introduces the basic structure that our RPC system provides. Since we have transparency between local and remote objects in process on the same machine and over the network, what we need is a proxy object that the client sees which looks the same as the object, irrespective of which case is being used. Similarly, in the server side, in the case of remote objects, we have what we call a stub object which looks to the server object just like the calling client. The proxy marshals the parameters for the method calls and sends them to the stub, which unmarshals the parameters and makes the call. Marshalling code is needed for each method signature or prototype in the system. OLE groups marshalling code on an interface basis. The next diagram dives into detail of how these proxy objects and stub objects are constructed. The first thing to notice is that I have several sub-objects that collaborate to provide the functionality of these proxies and stubs. The reason for this functional separation is simply that our model supports multiple interfaces on an object and extensibility of the set of interfaces in the system. We therefore need a mechanism to install marshalers for interfaces that are added to the system. By factoring these into separate objects, we can leverage our component object model and the dynamic loading mechanism to provide this ability without having to add a new mechanism that does it specially for the RPC system. By making this lightweight enough to make small objects efficiently supported, we can model all kinds of components, such as these marshalers, as objects in the system. Our marshalling system treats interface pointers or object references as fully supported data types in the system. They can be transported around, passed as parameters of method calls between one process and another or between one machine and another. What happens when one of these pointers is passed as a parameter is that the sending side establishes the stub object and transmits the address of that on the wire to the other side. The receiving side then instantiates the correct kind of proxy object and establishes connection back to where the object really is. There are variations of this that deal with connecting between three-party interactions, where if one object has a reference to a second object in another environment and passes a reference to a third object, that third object will end up with a direct connection to the one providing the service. This diagram is showing one of the features that we have in our marshalling system that allows an object to take special action when it's being marshaled into another context. The object, optionally, is called to marshal itself. It can then determine what class will run in the receiving process and what data it will be initialized with. Objects can exploit this to provide optimized communication when they are marshaled. They can do things like batching and filtering of method calls, and they can exploit shared memory to support communication between the two processes in the case that shared memory is available. Our compound file storage does this. When two objects are accessing the same storage medium, our compound file implementation will use shared memory in the case that those two objects are running on the same machine. This provides much greater efficiency in those cases, but doesn't prevent these things being distributed. In our model of persistence, a container will create or obtain somehow a storage resource, which may be the default compound file implementation supplied by OLE, or may be one supplied by that container itself. The container then gives this storage resource to the object to read and write its data. The container and object cooperate on when to save, when they've completed, and the container commits the transactions finally. This is an example of collaboration where the object is parametric with respect to the storage that it uses. The container assigns the storage resource, the object uses it, and there is a separate interface for them to negotiate over their use of this resource. There are many other examples like this, but this one is particularly representative of that design theme. Moving on to talk about containment and naming. With the OLE architecture, we're trying to solve the problem of an evolving world. We need to deal with past history and future services that are going to come into being. In order to deal with naming in this world, we have come up with a scheme for federating different namespaces. Clients can use names irrespective of the namespace they belong to. Different namespaces typically have different binding methods or function calls and different kinds of parameters that you supply. They might be string names to files, they might be offsets within some data structure or keys within the database or various other examples. What we have done is to provide an encapsulation that we call a moniker. A moniker encapsulates the type of container, the binding method that's used to extract things from that container, and the parameters that are needed for that method. The moniker exports a standard interface for binding to the resultant objects. Monikers are composable so that we can make hierarchical paths out of them, analogous to file system hierarchical names. The key elements of this design are that the clients see an abstraction, which is save, load, compose, decompose, and bind. They don't see the implementation. So some third party can create the moniker to refer to a particular container and give it to some client, who can then bind to the resultant object without knowing where it lives or how it's implemented. This allows us to take existing software and connect it to objects that live in new domains and new namespaces without changing that existing software. And it's another example of the kind of three-way collaboration between creating a resource, giving it to an object, and having that object use it. Another piece of the design that shows some examples of these design themes is the model that we have in OLE for uniform data transfer. First, we have a common interface for transferring data and for requesting change notifications. This is used in many different scenarios. The first point to note is that this represents a collaboration between the data source that implements the basic transfer interface and the sink that receives notifications. This interface is reused in different scenarios, such as clipboard transfer, drag-drop, and programmatic access, where a client binds directly using the naming scheme to the data source. The key point about this is that by reusing the interface, we reuse the design, and we allow both the source and the sink of data to reuse that transfer code in all these different scenarios. They can write this transfer code once, add a little piece of code to support the drag-drop that provides the initial connection, and thereafter use the same code as they used in the clipboard transfer support. This gives us reuse of code for the developer. It also gives us much more uniformity of implementations, so that the end user expectations that the same transfers will work the same way will be satisfied. One of the things we did with OLE was to take a vertical slice through a particular application domain so that we could provide useful functionality as well as low-level building blocks. We chose compound documents as the first such application domain. There are several purposes behind this. First is that it provides immediate value to people in our first release. We don't have to provide technology that then someone else has to build things on before it's ever of any value to anybody. It helps us to build a population of objects so that future objects that we build can interoperate with those and add value to them. This provides us a way to bootstrap the marketplace for objects. There are many objects out there that can provide people a new way to introduce new objects and sell them into that market. It also provides us a test case to ensure that our technology in the underlying layers has the right flexibility and the control that is needed to build real applications. We have found in the course of doing this that we had to add things at the lower layers, such as concurrency management features, which are not present in other object-oriented systems of this kind. Without these features, it's not possible to build real live applications of the quality that people expect. At this point, I want to show a demonstration of the kinds of compound document functionality that we get by using this technology. In 1992, Bill Gates showed a demo that was a user interface prototype of what we thought OLE was going to be. And some of you may have seen that demo, and so you'll recognize this. It was a quarterly statement by Starbucks Coffee Company to their shareholders. It was a compound document with images, sounds, charts, spreadsheets, and so on in it. What I've done here is to recreate that using real applications to create a real compound document that looks and feels the same as that mock-up. So here is the overall view. What I will do is zoom in. Ooh. And so here we can see various different kinds of graphic embedded in the document. This particular one is a combination of a spreadsheet for calculations and a graph. And when I decide I want to make changes to this document that I'm working on, I simply activate that object, and what will happen is that the surrounding tools around the object will change to be the ones appropriate for that kind of object. So now what we can see is I have the row and column headings that are familiar from Excel. I have a formula bar that I can insert values into. So I can come down here, make a change to this. Let's suppose I'll change this to 78,000. And we will see the number changes, the graph updates accordingly, and I can move on to my other pieces of work. So what we've done here is to take the original vision of what the compound document should look like and how the user should interact with it, and we've made it real using the OLE architecture. Okay, for this demonstration I'm going to show a custom application for monitoring stocks and news and by executing trades. What I have is a screen that's showing me the current values of the stocks, and I have a news service that will show me the most recent news clip that we've been able to get from the video server. So let's take a look at the most recent bit of news.
At Starbucks company headquarters in Seattle, they say roasting coffee is a lot like spinning straw.
In this case, the news clip is about the Starbucks Coffee Company quarterly earnings results. So perhaps based on the news that I've seen here, I'll decide to go and buy some Starbucks stock. So I'll come over to this button and create a transaction which will send off a request to my stockbroker to buy stock at the end of the day. Let me switch to my mail to show you that. So over here in my outbox, I have this mail message to my stockbroker asking to buy 220 shares of Starbucks. Let me come back now and show you how that works. What I have here is the embedded video player object. I have the stock data that's being shown to me here, the button that triggers the transaction processing, and this interesting little envelope object. This envelope object is a special purpose object that knows how to construct and send a mail message and can be driven by OLE automation, and I'll show you the code that's used to do that. Over here, I have some Visual Basic for Applications code, which is talking to that envelope object to set up the subject line, the to line, and the body of the mail message. And down at the bottom is executing a simple method invocation on that envelope to send the message. And with the result that you saw, that the message was dumped into my outbox to be sent out at the appropriate time. This custom application is built using OLE automation, Visual Basic for Applications, and Excel. These are all products that are available today and have been put together with a custom object built by somebody for their particular purpose of communicating with mail. The final demonstration that I'd like to show you takes us into a new area. The previous demonstrations have shown integration of objects with documents and integration of objects with the environment in the mail message example. This demonstration is taking us in the area of functional integration between objects. The example that I have here is a database application. In this case, I'm using Microsoft Access. What I have is a table of products and suppliers and appropriate information about those products and suppliers, such as names and addresses. Finding things in these tabular databases, it can be very difficult, and query languages are very daunting to people to use. So what we've done is we've created a different way to organize this information, which is done hierarchically as shown in this top left pane here. But what I have is I've grouped my products by the suppliers and the product names underneath them, and I have a hierarchical navigation scheme to drill down and find the products that I'm interested in. And as I click on these entries, these other forms are showing information about the company that's supplying the product and the product itself. And as I click around, these things are updating to reflect the appropriate thing. Now, the interesting thing about this is that this hierarchical navigation pane is an OLE object. It's an extension of an OLE object that we call an OLE control, and I'll be talking about that and how it all works later in this talk. The interesting thing about it is that it can be added into any OLE-aware application, and it can be added with particular effect into any application that understands OLE controls and events, which are the means by which this control communicates to the other objects. Let me show you one or two things about this control. If I switch to the Forms Design mode, where I can see here I have this data outline control, and I can look at its properties. The way that this control works is that it allows me to specify for the different levels of hierarchical containment things like the name to show what data to select and how that data should be displayed in that outline control. So I can select different things for level 1 of the hierarchy, level 2 of the hierarchy, and so on. In this case, I only used 2 levels. I also, up at the general set of properties here, is that I have the ability to specify whether events should be sent to the container about the form and the activities that are going on this outline control and about movement of the focus within that control. These events are what is used to coordinate the activities with the other forms on this display. So this shows you the kinds of functional integration that we can get with OLE as we move forward and add new capabilities to it. When we come to put all these design themes into practice, we run into a number of additional issues to deal with, which I will just mention in passing. One is that objects, because they're persistent, can be moved around. I can copy one to a floppy disk, send it to my friend in Japan, and so on. This raises issues about the availability of the codes needed to support those objects, and it raises issues about interchange. If different people have different choice of applications, then they need ways that these objects can be interchanged between those different editors or applications. Another point is reliability. If I have a system composed of some thousands of objects, the probability of system failure is the probability of an object failure multiplied by 1,000. This means that we must have extremely high reliability objects in order to build a system of this sort. In addition to that, the testing burden is increased by the configurability of an object in these parametric designs. Objects must be tested against different instantiations of the resources that they're using. Altogether, this amounts to a large quality assurance program, and we expect over the coming years to find better ways to tackle these kinds of problems. Factoring systems into objects of smaller granularity and having strict definitions of the interfaces will make exhaustive testing of objects more tractable. I want to talk for a short while about some real applications that are being built using this system. Obviously, we have a number of retail software applications in the productivity tool category, such as word processors and spreadsheets. But I'm talking about applications in the sense that an end user thinks of them, something that satisfies that user's task or running that customer's business. One example we have is an auditing system that's being developed. They're using a number of retail productivity tool objects, adding some objects to do auditing specific things, such as monitoring two different numbers to make sure that they're the same and flag them if they're different. The whole thing is being put together with a compound document management system and will be used to support many tens of thousands of auditors in the field. Another example that we have is a customer who is rebuilding their branch banking software. This will involve creating some thousands of classes that are all dynamically connected using the OLE architecture to actually run their bank. A final one I want to mention is market trading system, where brokers will have workstations that show market trading data, newswire information, and so on. And they can couple these together with analysis tools like spreadsheets and graphing tools. These systems are now being redesigned using the OLE architecture so that they can get integration with desktop productivity objects that are available and also hook them up to specialized services such as real-time stock data. I'm now going to talk for a little while about the kinds of developments that are going on during 1994, 95, and 96, about enhancements and extensions to this overall architecture. There are a number of areas to cover, including distribution on the network, integration of storage and data with the file system, events which are used to support our forms and controls model, and richer document integration so that our compound documents can become more interesting. First, I want to talk about distribution over the network. Recalling our earlier slide on the RPC architecture, we can now see why factoring into separate sub-objects is so interesting. I can replace just two of the objects in this overall picture with variants that use a standard interoperable network RPC mechanism, and I get transparent distribution without changing the other parts of this architecture. Similarly, we can start to use standard tools for building marshallers for custom interfaces, and we already have an architecture where the output of those tools can be installed into the system. I mentioned this in passing earlier. In the area of richer document integration, we will be defining additional interfaces which exploit the OLE architecture's ability to add interfaces into the system. New interfaces will support things like text extraction for spell checking and indexing, property inheritance so that objects can take on the look of their container, layout negotiation for complex page layouts and page breaking, and an add-in architecture so that add-in objects that use OLE automation to extend the functionality of a particular document or system can be added into an application product and co-reside with other add-ins in a robust fashion without colliding with each other. In addition, there's some additional work for multimedia support to do such things as management of time, synchronization of multimedia streams, and scheduling activities. Events are one of the more interesting and important things that have been developed. The notion is that some object can fire an event. This is an outgoing call that the object makes at certain times during its execution. These calls are made to some other object that we call the event sink. Event sinks are connected dynamically through connection points on the original event source object. These event sync interfaces are just standard interfaces in the OLE component object model definition. That is to say, they are contracts. This design is leveraging the existing component object model design. Our connection point interface is a counterpart of the query interface functionality that was described earlier. This diagram shows schematically what it means to make a connection. The event source object on the left has an interface for establishing a connection. Once the connection is established, this object will, at the appropriate point in its execution, make a method call on the event sync. The nature and the method call and the signature of the parameters is part of the contract of that event sync interface, and therefore of the object that fires the event. Using this event model allows us to use the OLE architecture to build forms and controls. Controls are visual objects that live on the form and provide particular kinds of user interaction, such as push buttons, text edit fields, list boxes, and so on. In this architecture, these controls are just OLE embedded objects with the addition of events. Forms are containers for these embeddings and have the ability to connect up to the events and receive notification from those controls. This forms model is independent of the development environment for programming that people will use to customize these forms. It represents a reusable technology and the basis for extensibility. Our forms package is something that people will be able to use by adding their own controls and/or reusing the controls that we supply. In the area of storage, we are making a distributed file system and directory service. But more interestingly, we're making an object file system, which unifies the storage notions for embeddings and for documents. This allows us to get greatly optimized performance, since we don't have two layers of storage management. It also allows us to add properties to documents and objects and containers. Properties that are not necessarily known to the objects themselves. They're like labels that are added onto the side. The system will provide indexing of the content in these objects and their properties. Content will be extracted through text extraction interfaces and filtering. This storage system will provide full interoperability and interchange with today's file systems and the compound file implementation that's in OLE today. Given this storage system and the indexing enables us to implement queries, a way to retrieve objects by attribute or content rather than by name or location, and to do this in a very efficient manner. In particular, in the distributed object file system, these queries can be processed at the optimal location. Instead of transferring the data to the client workstation in order to evaluate the query, we transfer the query to the server, execute the query there, and transfer the results back. This will make queries a natural way to retrieve information simply because it's efficient. In addition, the system will support link tracking and will introduce the notion of a query moniker, which is an encapsulation of a query which can be used as a name or a link to some object. The example I've chosen here is a query that encapsulates the notion of the closest printer to my office that my group is allowed to use. At the time of resolving this link, the query is evaluated and a particular printer is chosen. The value of this is that if I move office, I will get a new printer the next time I use this link. Or if I'm assigned to a different group for resource allocation purposes, I may get a different printer. But my link remains unchanged. So, to revisit the things that we've talked about and to try to put them into the overall framework, we can see that we're extending the system in a number of different dimensions, filling out the space of systems that can be built with this, simply by extending the OLE architecture and the component object model in the ways that it was originally designed for. Extending it by adding distributed RPC, by adding new objects, new user interface paradigms, and new interfaces. Beyond this, the sky is the limit. We really can't imagine all the ways that extensions can be added to this architecture and exploited in interesting and powerful ways. Thank you.